Refraction at a spherical surface. So here we are trying to derive a relation between object distance u, the image distance v, refractive indices n, and the radius of curvature r of a spherical surface. So here is a curved surface. This part I am looking at. This is curved, and this curved surface is a part of a bigger imaginary sphere, say something like this. So this is an imaginary sphere here, so to which this curved surface forms a part. So now this imaginary surface will have a center, so that is called the center of curvature. So this center is a center of curvature for this curved surface. So also this imaginary sphere has a radius, and that becomes the radius of curvature for this curved surface. So now to understand the refraction through this surface, and remember we are taking the surface, this medium, to be of refractive index n2, which is denser, which is more, this refractive index is more compared to n1, which is the refractive index of the surrounding medium. Like for example, this medium, denser medium, is glass, say, whereas the outer medium is maybe air or vacuum. So n1 is less than n2. So now in this case, to understand the image formation, so let us consider the principal axis first. So principal axis is a line which passes through the center of curvature C and the pole of the curved surface. So pole is of course the geometric center of this curved surface here. So now let us have a point object O on the principal axis, and this O is at a distance which is called object distance, so which will be measured from pole to the object. So that is u. U is the object distance here. So pole M to object O. So this is the object distance. Now whenever a ray of light emanates from O, hits the surface, say for example as shown here. So when a ray of light is incident on the surface from the object, now say this is point N on the surface here. Now this ray will undergo refraction as generally expected. So refraction is what? Bending of light due to change in its speed. Okay. So now the light has to be bent based on different factors, like whether it is traveling from rarer to denser, denser to rarer, and all that. So what is the bending to understand? You know, we need to have first a normal drawn at this point. So how to draw a normal for a spherical surface? It's easy. At n you want the normal, so just draw a line passing through n and the center of curvature, which is nothing but the radius of that imaginary sphere. So that itself is the normal, we can say. So here I will draw a normal, so at this point n. Then what is the angle of incidence here? This is the incident ray, and here is the normal. So angle between them is the angle of incidence, which is I, let me take. Now this ray, after hitting the surface at point n, instead of going straight like this, actually if there was no surface of separation between the two media, this surface, if this surface was not there, then the ray would have gone straight like this. But because of this surface, this ray now bends. So how will it bend? Will it go away from the normal or towards the normal? It has to go towards the normal only, because it is traveling from rarer to denser medium. So whenever a ray travels from rarer to denser medium, it will bend towards the normal. So normal is this. This is the actual ray, so incident ray. So this gets bent towards the normal, so in this manner. And it touches the principal axis. It hits the principal axis at some point as shown here. Now the normal to the refracted ray, the angle is angle of refraction. Okay, one ray of light incident and refracted we understood. Now let us consider one more ray traveling from O and hits the surface at M. So that is the ray which is very along the principal axis itself. So this ray of light, after hitting the surface at M, of course if you want to draw the normal, this C to M line itself is the normal. So therefore it is normal incidence actually. So angle of incidence is 0. The ray goes undeviated in this manner and also meets the previous ray at this point, that is I, where the image is formed. So object is O, I is the image. Now I is also at a distance M, at some distance from M, that is pole. So pole to I, this is called image distance, which we denote as V here. So V is the image distance, U is the object distance here in this case. So now this is the complete ray diagram to understand the refraction through a spherical surface. Now I'll drop a line from N onto the principal axis, that is ND, So just to understand the geometry of the diagram here. And also just remember that this MD is very very small for paraxial rays. Paraxial rays means rays which are very close to the principal axis. Means if n is close to m, somewhere here, say, when you drop a normal, you can see that MD is so negligible, so that we can ignore it. So D and M are considered to be same in all practical situations, assuming that the incident rays, the rays of light which are in consideration here are paraxial rays, means close to the principal axis. So now let us give some names for all these angles. Say NOM, M or D, it's the same thing. So NOM, I will name it as alpha, and NID or NIM. So this angle I will name as beta. NCM or NCD, this angle here I will name it as gamma. So these are the denotions I have taken for understanding the geometry of the diagram here. So here we have the diagram. Now let us try and understand the derivation of the equation between which relates this object distance, image distance, refractive indices n1 and n2, and the radius of curvature. So to start with, for small aperture, as I already told you, the aperture of this, the mirror is supposed to considered to be small, and this NOM angle, then NCM and NIM, these angles, that is alpha, gamma and beta, I will consider here. When the n is very close to m, that is for small aperture or paraxial rays, you can understand that this alpha, beta, gamma, they are all very very small. We can understand practically. So n, when it comes closer and closer to the principal axis, you can see that the bending decreases. So alpha is less, beta is less, gamma is less. All are very very small for paraxial rays. So in this case, for one by one I will take. Say tan of alpha I will take. Tan of alpha is equal to what? So generally tan is what? Opposite by adjacent. So therefore tan of alpha is equal to Mn by Om, but which is also equal to alpha itself, because I already told you alpha is very very small. Therefore tan of the angle is equal to the angle itself. So tan theta is equal to theta approximately for small angles of small values of theta. Therefore tan alpha is equal to alpha itself. Similarly for gamma here, so NCM is the triangle. In that, tan of gamma is equal to opposite by adjacent. So NM by CM or MC. So that is MN by MC. MN by MC, opposite by adjacent, which is also equal to gamma itself, because angle is very small. Similarly for beta. So MN by MI. This is angle beta. So tan of beta is equal to MN by MI, which is almost equal to close to beta, we can say approximately. So now let us try and understand the n in this triangle N, O and C. This triangle, if you look at in this triangle, this I is the exterior angle, you can say. So NOC, in this triangle I is the exterior angle. So this exterior angle is equal to sum of the opposite interior angles, so alpha and gamma. So I is equal to alpha plus gamma, we can say. So I is equal to alpha plus gamma here. But alpha and gamma, you know, alpha is Mn by Om, gamma is Mn by MC. So Mn by Om plus Mn by MC, we can say. Similarly for NIC, this triangle, if you look at this small triangle, if you look at here, in this triangle gamma is the exterior angle and opposite interior angles are R and beta. So gamma is equal to R plus beta, or R is equal to what? Gamma minus beta, we can say. So R is equal to gamma minus beta. I will take for R is equal to gamma minus beta, which is gamma is Mn by MC, beta is Mn by Mi. So why are we taking these things? Of course, we are trying to get relations for I and R here. Angle of incidence, angle of refraction, both we got now. Now let us apply Snell's law. Snell's law is what? N1 sin I is equal to N2 sin R. So N1 into sin of the angle of incidence is equal to N2 into sin of the angle of refraction. This is the standard definition, standard equation for Snell's law. Now let us substitute N1 into sin of I. I is what? Mn by Om plus Mn by MC. Similarly R is what? Mn by MC minus Mn by Mi. Okay, before that, what is sin I? Sin I, as I already told you, when n is very close to m for paraxial rays, alpha is small and also I will be small, because when n is close to the principal axis, I will also be small, R will also be small. Therefore, practically we can consider I and R to be so small that sin I is equal to I itself and sin R is equal to R itself. So for small angles, Ni is equal to N1 into I is equal to N2 into R, we can say. Now let us substitute for I from here, this equation, and R from the other equation here. So when I substitute that, N1 into I is equal to Mn by Om plus Mn by Mc from this equation here. So similarly is equal to N2 into R from here, Mn by Mc minus Mn by Mi. So this is nothing but Mn common taken out, here also Mn common taken out, cancels each other. So therefore N1 taken in, N1 by Om plus N1 by Mc, N1 by Om plus N1 by Mc is equal to similarly N2 by Mc minus N2 by Mi, we can say. Now in this, you can see here that Om, Mc, Mc is looking common. Om and Mi, if you look at, Om is what? Oh, object distance, okay. Im or Mi is what? Image distance. So let us take these two to one side. This N2 by Mi I will take to the left. This N1 by Mc I will move to the right. So I get N1 by Om plus N2 by Mi. This came left. Then N2 by Mc minus N1 by Mc went to the right. So Mc is common, so taken down here, common. Now in this, what is Om? Om is O to M is the object distance, and M to I is the image distance. But here we should use the sign conventions, the Cartesian sign convention we have to use. According to the Cartesian sign convention, okay, any distance, whether it is object distance, image distance or any distance, they are all measured from the pole of the surface. Also, the distances measured in the direction of the incident light are taken to be positive, and those in the direction opposite to the direction of incident light are measured to be negative. So therefore M to O is opposite to the incident light direction, so therefore is minus of U, which is negative. So minus U is the object distance, and M to I, which is V, which is positive. M to C, which is R, which is also positive, because R and V are in the direction of the incident light itself. So M to I, M to C, like that they are measured. So from the pole M to O, when I measure, object distance is minus U. So by using the sign conventions, OM is equal to minus U, MI is equal to plus V, MC, M to C, which is the radius of curvature, that is also plus R. So then by substituting N1 by OM is minus U, then Mi is V, MC is R, we get this equation. So this is the relation between the object distance, image distance, refractive indices and the radius of curvature for a spherical surface. Now how to remember this? What is N1? N1 is the outer medium's refractive index here, where object distance is also there. N2 is the denser medium's refractive index, where image distance is there. So easily we can remember it as object space refractive index N1 divided by object distance U plus image space refractive index N2 divided by image distance V is equal to difference in the refractive indices, that is N2 minus N1 divided by radius of curvature. So this is the relation between object distance, image distance, refractive indices and the radius of curvature for any curved surface, curved spherical surface. And this equation is, just remember, this is valid for even concave surface, not only convex surface which we have taken here. Even for concave surface, the same equation is applicable. So only thing is, based on the situation, this minus or pluses may change, so that you have to, while applying, you will understand. So now based on this, a question will be asked just to arrive at a relation between these factors. So remember, object space refractive index by object distance plus image space refractive index by image distance is equal to difference in the refractive indices by radius of curvature. So then the question based on this is, derive the relation between object distance, image distance, refractive indices and the radius of curvature for refraction at a spherical surface. This will be a 5-mark question. So this is the refraction at a spherical surface.